Hi everyone, and welcome back to physics. This is Mrs. Hutchinson, and today we're going to start our next unit where we're going to talk a little bit about motion. Today's really going to focus on motion and velocity. So let's get into it. Let's learn a little bit about the background of how we got to our current definitions. So, Aristotle, you may remember him from chemistry and his great contributions to our theory of the atom, how it kind of set us back. Well, he didn't quite do as terrible a job as explaining some of our physics references. So let's get into it. I mean, he really had to kind of explain how motion worked way back in 384 to 322, so way back when. But his attempt to classify what he saw, what he observed in terms of motion, well, what he did was he classified motion as natural and violent motion. Natural motion is what we see every day, what the objects do naturally, what their natural tendency is in terms of their movement. For example, a rock comes from Earth, so if it's taken away from Earth, it's going to fall back to Earth. Granted, he's talking about gravity, but he didn't know that. He was just saying the rock is naturally on Earth, so it wants to stay on Earth. Smoke comes from the air. Not really, but that was what he thought. Smoke coming from the air, therefore it naturally wants to be in the air, hence why it rises. So that was his definition of natural motion. So things naturally have a place, and that's where they want to be. Violent motion is something that doesn't occur naturally. We have to have these actual forces, pushing or pulling forces, on our violent motion objects. In other words, if we're talking about an arrow flying through the air, arrows don't just naturally fly through the air. We have to cause them to fly through the air. And his thought was that if an arrow is going to fly through the air, it must have a continued push by the air behind the arrow in order to maintain its flight. So, I mean, it kind of has some relevance-ish. I mean, it's a good attempt. And Aristotle taught that the normal state of objects was one of rest, basically, much like a teenager on a warm summer day. You know, one of rest, you want to rest, and that's the natural state of objects. Therefore, the Earth, if it's in its natural state, must also be motionless. Of course, we know now that's not exactly the case. Copernicus and Galileo added something to this definition. Of course, much later, in the 1500s. So Copernicus actually introduced his heliocentric theory, where the Earth revolved around the sun, which we now know is actually true. And he was the guy that actually said, okay, yeah, Aristotle was not right. The Earth is not motionless. In the 1600s, Galileo took Copernicus's theory and was able to discredit a lot of Aristotle's teachings. So yes, Aristotle, although he was this great pre-Socratic philosopher, I shouldn't say pre-Socratic, but he was this great philosopher in Greeks way back when. He didn't really help us for our explanations today. Galileo, but what he did was he went up the Leaning Tower of Pisa. Yes, it's been here since that long. And he demonstrated that objects of different mass, they fall at the same rate. Well, that's interesting. So he's basically saying they're accelerating the same amount, regardless of mass. So that's kind of interesting. He also used balls rolling on an inclined plane to support his hypothesis that the horizontal plane would neither speed up nor slow down in the absence of friction. So he is basically saying here that we are not experiencing acceleration in the horizontal direction. That's kind of interesting as well. We'll see if that holds true. Now, in an experiment with two inclined planes, Galileo proposed the concept of inertia. If you have heard of inertia, we're going to discuss it here. by suggesting that in the absence of friction, a ball rolling down one incline would keep rolling until it is slowed by an opposing incline. So he's actually correct. And if we remember what inertia is directly proportional to mass. And what do I mean by that? Well, heavier objects have more inertia, regardless of whether or not they're actually moving. Equal more inertia. Of course, we're going to discuss inertia a little more. But basically, if you have, say, let's see if I can fit it in way up here. Say we have 125 kilogram object, and it has no velocity. And we've got a 50 kilogram object that's moving at 50 meters per second. Which one's going to have more inertia? Well, the object that has the heavier mass. Because inertia is the ability to get an object moving, essentially. So, very, 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 very rough definition of inertia. We're going to get into that when we talk about Newton's laws. But what we need to understand now is that inertia is directly proportional to mass. Objects that are heavier will always have more inertia. Think about a Mack truck or something. It's a lot harder to stop a Mack truck that's going 60 miles an hour than it is to stop a little smart car going 60 miles an hour, because that big 18-wheeler has a lot more mass. Just think about it that way. Okay, so now let's take Galileo conducted experiments with smooth surfaces to demonstrate the effect of friction and to demonstrate that it can in fact be minimized. So he's basically saying, well, motion, it does occur with friction, and we can figure out a way to make things move a little faster if we just take out what he called friction. Now, Galileo's theories were not accepted by the Catholic Church. The Catholic Church actually accepted Aristotle's teaching, and he was put on trial for heresy as a result of publishing what he found for his experiments. So yes, again, Aristotle prevailed and put us a little bit behind. But that's okay. Let's talk about what Galileo actually described in terms of motion. He was the first to describe motion in terms of a time rate of change, which tells us how fast something happens. And here's what I want you to think about. Speed is an example of this time rate of change of position. In other words, it tells us how fast an object's position changes. If we have something moving at 65 miles per hour, that's telling us that we have changed our position by 65 miles in 1 hour. That's what I'm talking about in terms of time rate of change of position. Our position would be our mileage, and our time rate of change is how long it took us to make that change. Now, mathematically speaking, speed can be described as speed equals distance over time. And things that I want you to take out. If you do not have your reference tables out, please take them out. And I want you to flip to your mechanics section. So what I'm going to do is hopefully pull up our reference table. I can there it is. So here is our reference table. Here's the front of it. And I want us to flip all the way to the back. And if you take a look at the mechanics section, this is really where we're going to stay for quite some time. For the first half of the year is on this particular page. We're going to be looking at our very first equation here. So on the left side, we've got all of our equations. On the right side, we have the descriptions of all of the variables and the definitions of all the variables that correlate or correspond to all of these equations on the left side. So you'll be very familiar with this particular page. I do not want to save it. Okay, so let's take a look at our actual slides and let's see what we are dealing with. So again, what I did was I took our mechanics section, just kind of copied it down right here, and here's where you'll see all of the variables, so you can note that I pulled them directly off of our reference tables themselves. Now, speed will always have units of distance per units of time. So it could be miles per hour, it could be meters per second, it could be kilometers per hour, and it is your job to figure out how to convert between these particular types of units. Now, very often in real motion, the speed of objects vary while they're in motion. Basically, it's because you have to accelerate, or just think about it in terms of driving. If you don't have cruise control on, chances are you're probably going to fluctuate your actual speed or velocity. So just think about it logically in that sense. Now, because of it, it's useful to actually define average speed during a defined trip. So mathematically speaking, that's where we would get our equation that's on our reference tables. V with the line over it talks about our average speed, which equals distance over time, or displacement over time, and we're going to actually talk about that. Now, in physics problems, what we actually use as opposed to the average speed, what we tend to do is we tend to take what's known as the instantaneous speed. The instantaneous speed of something is basically how fast it is going at that particular instant in time. And again, to represent the average speed, we will either have the bar over it or V average. To instantaneous speed, it's just simply the V. Just to note the differences between those different notations. So now what I'm going to do, we're going to try a sample problem. Now, I know that you can do this in your head. By reading this particular problem, you're like, this is easy. I don't know why she's even having us do this. I already know the answer. And me personally, haven't even read the problem to you. But don't write anything down yet, because I want to show you how I want you to write every single problem for physics this year. So what we're going to do, what is the average speed of a cheetah that sprints 100 meters in 4 seconds? Pretty simple. But here's what I want you to do. We write down our given. What that means is that's where we find what's in the actual problem, and we define them. So we've got our distance, which equals 100 meters. And we've got our time, which equals 4 seconds. That's our given. We pulled that directly from the problem. This is what I want you to do every time, because a lot of times there's given information that's hidden in the problem by just words that they use. So it's very important to write down what's given. Next, we write down our wanted. So wanted means, what are we trying to find here? Well, here it says, what is the average speed? So that's what we're trying to solve for. After we've written our wanted, what we're going to do, we'll write down the equation or equations that we're going to use to solve this particular problem. If we take a look at our givens, we've got distance and we've got time. And we want to solve for our average speed. There's an equation that actually incorporates all of those variables. So that's the one that we're going to use. You'll notice on the mechanics section there's a bunch of different equations. You are going to use multiple equations at one time. You might have to combine them. So it's kind of important to figure out what equation or equations you are going to use. Next, we've got our substitution. If I can spell. Yes, I can. Substitution is extremely important in physics. When you are substituting, you have to substitute with units. Always, 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 if you do not substitute with units, you will not get any credit for that substitution. So please, always put the units in there. So, we've got our average speed or velocity. We've got our 100 meters over 4 seconds. That's our substitution. And the very last step would be our answer. You have to have your answer with units as well. So our answer in this case would be our average speed is 25 meters per second. Okay? This is how I want you to set up your answers for every single problem that we do when it deals with math. Okay? You must have your given, your wanted, your equation, your substitution, and your answer. Now, of course, you can abbreviate it by just putting G and W, E, S, and A, that kind of thing. Okay, but please, 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 this is how I want you to do it every single time. Of course, that was not so bad. And then it says, next part of the question is, how about if it sprints 50 meters in 2 seconds? If you were to do this all over again, the only difference would be here. We would change this to 50 meters, change that to 2 seconds. We change these to 50 meters over 2 seconds, and of course you'd wind up with the same answer. Okay, not too bad. Now what I want you to do is pause the video and try question 3 on your own. Read through it. In this particular instance, for this particular problem, you can, and I would if I were you, write down your givens and your wanted and so on and so forth to solve for each section. So go ahead, pause the video, try question 3, make sure you're substituting with units, make sure that you're giving me an answer with units, and then I'll show you how to do it when you come back. So, taking a look at question 3. Hopefully, you paused the video and you tried it on your own. So it says, if a car moves with an average speed of 60 kilometers per hour for an hour, it will travel a distance of 60 kilometers. How far would it travel if it moved at this rate for 4 hours? Okay, so A. We have our given, our average speed, 60 kilometers per hour. Our time is 4 hours. Our wanted is our distance. Okay, so our equation that we're going to use, V equals D over T, substitution, 60 kilometers per hour. Again, substitute with units, please. 4 hours. Our answer, of course, if you don't know how to solve for that, please make sure that you do, because I'm assuming that you know that math. Cross multiply there, and you should have gotten a distance of 240, and our units for this would be kilometers. Hopefully you did that, and you did that pretty well. Let's try part B. Okay, so part B, we've got our given. Again, our average speed or velocity is 60 kilometers per hour. Our time, 10 hours. Wanted is our distance. Equation remains the same. V equals D over T. Let's plug it in for our substitution. Please, 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 please plug in with your units. If you don't plug in with your units, you will definitely fail this course, even though you may know everything. Cross multiply, and you should have, for our distance, of 600 kilometers. Perfect. So next, it said, would it be possible for the car that starts from rest and ends at rest to attain an average speed of 60 kilometers per hour and never exceed a reading of 60 kilometers per hour? The answer for this one is absolutely not. Things you want to think about: we start at 0, we add in all of our instantaneous velocities until we get all the way to our final velocity of 0. Divide them by all of our instantaneous, or the number of velocities that we took, and that will always be less than 60. Our maximum speed, if our maximum speed is 60, if we add 60 and 0, you will never obtain an average speed of 60. Plain and simple. Okay? So let's take a look. What I want you to do is pause the video now. Try question number 4. Again, do your givens, your wanted, your equations, your substitution, and your answer. So go ahead, pause the video, try the next one. I'm going to show you how to do it after you come back. Hopefully you paused the video. And now I'm going to show you how to do question number 4. During a race on level ground, Susie covers 825 meters in 137 seconds while running due west. So we will definitely get into that, has something to do with it a little later. Find Susie's average speed. So here's our givens. Got our distance equals 825 meters. Our time, 137 seconds. And our wanted says our average speed. So, bam. I know you're like, this is tedious, I can do all these in my head. Trust me, you're going to love me for it later, I promise you. Our equation, V equals D over T. If you're not practicing doing all of this, it's going to come back to bite you, so please, please, please make sure you're practicing doing all this. Substitute with units. Don't get lazy on the units, please. Don't know how many times I can say that. Do a little bit of Mathematica. And your velocity should be 6.02 meters per second. And I got meters per second because looking at these units here. Hopefully you did that, and hopefully you did that pretty well. If you didn't, go back and check the video and see where you can improve or see what you may have missed. What I want you to do now is pause the video, try question number 5 on your own. Again, given, wanted, equation, substitution, and your answer. So go ahead and do all that. So now hopefully you pause the video, and I'm going to show you how to do question number 5. Bicycle rider travels 22 kilometers in 3.25 hours traveling northwest. The average speed in kilometers per hour and in miles per hour. Okay, so we want 2 different answers here. Here's our given. Distance equals 22 kilometers. Time, 3.25 hours. Our wanted, average speed. Our equation, which I'm going to put down here. Oh, that's silly. Let me get that out of the way. Our wanted is our average speed. I wrote our equation in the wanted section. Here's our equation, D over T. So now let's substitute it in. We've got 22 kilometers over 3.25 hours. Again, substitute with units, please, or else it's going to be very bad for you in the long run. And here is our answer in kilometers per hour. To convert from kilometers per hour to miles per hour, the conversion factor that you're going to be using would be 1 mile equals 1.6 kilometers. Of course, I would have to give that to you, but we have been using it pretty recently, so my guess is you probably or may have remembered using it. So let's go ahead and convert. So we've got 6.8 kilometers over 1 hour. So 1.6 kilometers, 1 mile. Kilometers crosses out. And we're left with 4.25 miles per hour. Okay? If you forgot how to do that conversion, go back and check out that video that talks about it. So please, please, please go ahead and do that. I want you to make sure you stay on top of things. Next, what we're going to do, well, yeah, I know, you thought you were done. Nah, no way. You're silly. Definitely silly. Let's talk a little bit about speed and velocity and scalar and vector quantities. We definitely will have an entire unit on vectors, but what I want us to do is kind of get into it a little bit, and it will be somewhat of a discussion. So if you need to take a little bit of a break from listening to this glorious voice of mine, go ahead, pause the video, stand up, shake it off, and get back to it. Okay? So, very often in physics, speed and velocity are used interchangeably, but actually they're not really the same thing, which is kind of weird. Speed, as we've described it so far, is actually considered to be a scalar quantity, which means it only deals with the magnitude of the quantity that is considered. When I say magnitude, I'm actually talking about if we're saying that you're going 65 miles per hour, we're talking about the number in front, 65. That's the magnitude. That's what speed is really referring to. So speed is known as a scalar quantity because it only considers the magnitude. Velocity is a vector quantity because it considers the magnitude and the direction. So the difference is we're now going 65 miles per hour west. What makes this quantity a vector quantity is we now have a direction associated with it. We are moving west. We're not just moving at 65 miles per hour, but you're giving us a direction that's associated with it. So, speed, scalar, velocity, vector. Okay, so they both start with what they're associated with, which is kind of nice. So again, here's the example. If we say that an object is traveling at 75 kilometers per hour, that's a scalar quantity and describing our speed. If we're saying you're moving 75 kilometers per hour west, of course, I had to choose the same direction. It could be east, it could be northwest, it could be southwest, it could be any direction. But as long as there is a direction associated with it, we are talking about a vector quantity, and therefore this 75 kilometers per hour west is now describing an object's velocity. So I do need you to recognize the differences between a vector quantity and a scalar quantity. Vectors have speed, have magnitude and direction. Yes, they're going to kill people, direction and magnitude. If you've ever seen Despicable Me. Scalar quantities only have magnitude. So now, in that blank section below this particular area in your notes, I want you to write quite a bit of stuff. So get out your pen, you're going to need that. Okay, so as you can see, I paused this and I wrote in everything that I would like you to write for the bottom half of our speed versus velocity section. So what you can do if you want to is just simply pause this video so you can record everything and then listen to me explain it, or you can write it down as we're going, whatever works for you. If you find that as you're writing it and you're trying to listen and it's not really working, just pause the video, get everything down, and then start it back up again. So here's what we're talking about in terms of vectors and scalars. So distance is defined as how far something travels. Again, just so you know, I'm starting in the upper left corner. I'm starting right up here. Okay. Hold on. So now that I got all this back, I'm just going to tell you that we're starting in the upper left corner. I'm not even going to try and write on this thing. So, okay. Anyway, so distance, scalar quantities versus vector quantities. So our distance tells us how far something travels. That is a scalar quantity because it doesn't tell us what direction in which that thing is traveling. So if we take a look, average speed, as we just found out, average speed is a scalar quantity. So speed is defined as, and I'll just have you know that I'm looking right here. Okay. Average speed is defined as distance traveled over elapsed time. Average speed is just how fast something is moving as opposed to how fast something is moving in a given direction. So here on the right, if I give us, we'll do a little gray. So if we take a look over on the right side, it says distance measures actual path taken. So if you get up and you walk around a table, so let's just say you're starting right here, and you walk all the way around the table. The distance measures how far you actually physically walked from start to finish. You covered a distance of 5 meters. So when we are calculating, if you covered that distance of 5 meters in, say, 2 seconds, we can calculate your average speed to be 5 meters over 2 seconds, so our average speed would be 2.5 meters per second. The distance just simply tells us how far you travel. Speed tells us how fast you have moved while you were traveling. Displacement, on the other hand, is how far something travels in a given direction. And we use displacement because displacement is a vector quantity, so it's a vector quantity, whereas speed is a scalar quantity, or distance is a scalar quantity. Displacement, being a vector quantity, means that we're going to use it to help determine other vector quantities. So our average velocity is equal to displacement over time. So velocity is how fast something is moving in a given direction. So if we take a look at our table again, displacement measures the shortest path from start to finish. In other words, we walked all the way around our table. We covered a distance of 5 meters, but our displacement, how far we actually moved from start to finish, was only 1 meter. Okay. That's how far we were displaced. And in fact, if we were to do this correctly, our displacement is actually moving always from start to finish. So our arrow should point from start to finish. Our displacement equals 1 meter. So therefore our average velocity, if we took 2 seconds to cover this giant distance, our average velocity is 0.5 meters per second. So there is a major difference between vectors and scalars. Distance means how far you actually moved. Displacement means how far did you move from start to finish, where you started to where you ended, not the path that was taken to get there. So the next question is it possible to travel a great distance and have an average velocity of 0? The answer to that is, why, yes. Yes, it is. Average velocity implies path. It's independent of path taken. Basically what that means is where you start and where you end up. So we have to figure out how we can get that to be 0. Well, think about here's you. You decide to walk in a circle. You started at that dot and you ended at that dot. Your displacement is 0. Therefore, since your displacement is 0, it doesn't matter how long it took you to get there. Let's just say 5 seconds. Your average velocity would be 0 over 5. So your average velocity would be 0. If you start and end in the same place, your average velocity is 0. However, your average speed would have some sort of magnitude associated with it. So that's the difference between scalars and vectors. If you're a little confused by that, go ahead, pause it, rewind it, start again. Again, I do want to make sure that you are in fact aware of this over here, that our vector should point from start to finish. You always have your tail end of your vector where you start, and it always points towards where you end up. All right. So, I hope you enjoyed this video, and I will see you for our next one.